Look up at the night sky. What do you see? Twinkling stars, distant galaxies, the vast expanse of the cosmos. We perceive a universe filled with objects separated by space interacting over time. But what if this perception is an illusion? A simplified projection of a far grander reality? What if the universe's true nature is hidden? A deeper layer of existence beyond our immediate senses? This is where string theory, a revolutionary idea in physics, comes into play. It challenges our fundamental understanding of the cosmos and offers a glimpse into a reality stranger and more beautiful than we could have imagined. For centuries, we believed atoms were the smallest, indivisible building blocks of matter. These tiny entities were thought to be the fundamental components that made up everything in the universe. Ancient Greek philosophers like Democritus first proposed the idea of atoms, envisioning them as solid, indestructible units. This concept persisted for millennia, shaping our understanding of the material world. Then we discovered even smaller particles within these atoms, like electrons and quarks. The advent of quantum mechanics in the early 20th century revolutionized our perception of the atomic world. Scientists like Niels Bohr and Werner Heisenberg unveiled the complex inner workings of atoms, revealing a zoo of subatomic particles. These discoveries showed that atoms were not indivisible after all, but rather composed of even tinier constituents. But string theory takes us a step further, suggesting that these particles are not point-like objects but rather tiny, vibrating strings of energy. This groundbreaking theory emerged in the late 20th century, offering a new framework for understanding the fundamental nature of reality. According to string theory, the different particles we observe are simply different vibrational modes of these fundamental strings. This idea has profound implications for our understanding of the universe. Imagine these strings like the strings on a violin. Just as a violinist can produce a variety of musical notes by changing the way the strings vibrate, the fundamental strings in string theory can vibrate in different ways to create different particles. This analogy helps us visualize the abstract concept of vibrating strings in a more tangible way. Just as a violin string vibrates at different frequencies to produce different musical notes, fundamental strings vibrate in different patterns, creating the unique properties of every particle we observe. Each type of particle, whether it's an electron, a quark, or a photon, corresponds to a specific vibrational pattern of a string. This elegant idea unifies the diverse array of particles in the universe under a single theoretical framework. An electron is no longer just a point with a negative charge, it's a specific melody played on a fundamental string. This perspective transforms our understanding of particles from static, isolated entities to dynamic, interconnected vibrations. The properties of an electron, such as its mass and charge, are determined by the way its string vibrates. This musical metaphor highlights the beauty and harmony underlying the fabric of reality. This revolutionary concept changes everything. It challenges our traditional notions of space, time, and matter, suggesting that the universe is fundamentally composed of vibrating strings. String theory also offers the potential to unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, into a single coherent framework. This unification has been a long-sought goal in physics, and string theory brings us closer to achieving it. If particles are like notes, then the universe is not an assembly of static objects, but a dynamic symphony of vibrating strings. Each string contributes to the cosmic melody, creating the rich and complex tapestry of the universe. This perspective invites us to see the universe not as a collection of separate parts, but as an interconnected, harmonious whole. The music of strings offers a poetic and profound vision of the cosmos, where every particle and every force is part of a grand, unified symphony. String theory proposes a radical idea. Our universe has more dimensions than we can perceive. This theory, which has captivated the minds of physicists for decades, suggests that the fabric of our reality is far more intricate than it appears. While we are accustomed to thinking in terms of 3 dimensions of space and 1 of time, string theory opens the door to a world where additional dimensions exist, hidden from our everyday experience. We experience 3 spatial dimensions: length, width, height, and 1 dimension of time. These dimensions are the fundamental building blocks of our perception, allowing us to navigate and understand the world around us. From the moment we wake up to the time we go to sleep, our lives are governed by these 4 dimensions. We measure distances, calculate volumes, and keep track of time, all within this familiar framework. However, string theory suggests the existence of additional spatial dimensions curled up and hidden from our view. These extra dimensions are not just theoretical constructs, they have profound implications for our understanding of the universe. Imagine dimensions so small and compact that they are beyond the reach of our current technology to detect. Yet they are there, influencing the very fabric of reality in ways we are only beginning to comprehend. Imagine a tightrope walker moving along a cable. To the walker, the cable appears as a one-dimensional line, a path to be followed. The walker is aware of the length of the cable but not its thickness or any other dimensions it might possess. The tightrope represents our familiar three dimensions. Just as the tightrope walker perceives the cable as a line, we perceive our world in three dimensions. We see objects as having length, width, and height, and we move through time experiencing events in a linear sequence. But an ant, small enough to perceive the cable's thickness, can crawl around it, experiencing an additional dimension. To the ant, the cable is not just a line but a surface it can explore in multiple directions. This analogy helps us grasp the concept of hidden dimensions. Just as the ant experiences more dimensions than the tightrope walker, string theory suggests that there are dimensions beyond our perception, influencing the universe in subtle yet significant ways. These hidden dimensions, though invisible to us, are not arbitrary. They are intricately woven into the fabric of the universe, playing a crucial role in the laws of physics. The existence of these dimensions is not just a mathematical curiosity, it is a fundamental aspect of reality that shapes the behavior of particles and forces. They are crucial to string theory, shaping the vibrational patterns of the fundamental strings and thus dictating the properties of particles and forces in our universe. The way these strings vibrate in the hidden dimensions determines the characteristics of everything from the smallest subatomic particles to the largest cosmic structures. This interplay between dimensions and vibrations is what gives rise to the rich tapestry of phenomena we observe in the universe. Like the shape of a musical instrument influences the sounds it creates, the geometry of these extra dimensions determines the fundamental laws of physics. Just as a violin or a piano produces different notes based on its shape and structure, the hidden dimensions of the universe shape the fundamental forces and particles that govern everything we see. Understanding these dimensions is key to unlocking the deepest mysteries of the cosmos, revealing a universe far more complex and beautiful than we ever imagined. Think of the universe as a vast, intricate symphony. The fundamental strings are the instruments, each vibrating at different frequencies, producing a unique note. These notes blend together, creating the particles that make up everything we see and experience. The laws of physics that govern the universe are the score, dictating how these notes harmonize and interact. The universe, in this view, is not a random collection of objects but a perfectly ordered, harmonious composition. And what is the music this cosmic orchestra produces? It's the very fabric of reality, the forces that bind atoms, the interactions between particles, the birth and death of stars, the expansion of the universe itself. Every phenomenon, every process, every interaction is a part of this grand cosmic symphony. One of the most significant goals of physics is to find a single, elegant theory that explains all the forces of nature. This quest has driven some of the greatest minds in science for centuries, from Isaac Newton to Albert Einstein, and continues to inspire physicists today. The idea is to unify the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into one comprehensive framework. Such a theory would not only deepen our understanding of the universe but could also lead to revolutionary technological advancements. Currently we have separate theories describing gravity, Einstein's theory of general relativity, and the other fundamental forces, the standard model of particle physics. Einstein's theory has been incredibly successful in explaining the large-scale structure of the universe, from the orbits of planets to the bending of light around massive objects. On the other hand, the standard model has been equally successful in describing the behavior of subatomic particles and the three other fundamental forces. However, these two pillars of modern physics don't quite fit together seamlessly, but these theories seem incompatible, like pieces of a puzzle that don't quite fit. The equations of general relativity break down when applied to the quantum realm, and the standard model doesn't account for gravity. This inconsistency has led scientists to search for a more fundamental theory that can reconcile these differences. The challenge is immense, requiring not just incremental advances but a paradigm shift in our understanding of the universe. String theory offers a tantalizing possibility, a unified theory of everything. It proposes that the fundamental constituents of the universe are not point particles but tiny, vibrating strings. These strings can vibrate at different frequencies and their vibrations correspond to different particles and forces. This elegant idea has the potential to unify all the forces of nature within a single theoretical framework. By describing all forces and particles as vibrations of fundamental strings, string theory has the potential to bridge the gap between gravity and the other forces. It suggests that gravity is not a separate force but a manifestation of the same underlying principles that govern the other forces. This could provide the long-sought-after link between general relativity and quantum mechanics, offering a more complete picture of the universe. Imagine a single equation, elegant and profound, that encapsulates the workings of the entire universe, from the smallest subatomic particle to the largest galaxy cluster. Such an equation would be a crowning achievement of human intellect, a testament to our ability to understand the cosmos at its most fundamental level. It would not only answer some of the deepest questions in physics but also open up new avenues for exploration and discovery. This is the ultimate dream of string theory, a dream that continues to motivate physicists in their quest to understand the universe at its deepest level. The journey is far from over, and many challenges remain. But with each new discovery, we move a step closer to this grand unification, bringing us nearer to a complete understanding of the cosmos and our place within it.